Now that we know where charges come from and how they sort of interact with each other through Coulomb's law, we can actually start talking about how to get charges onto things and what types of materials will hold a charge really well or take charge really well, and what kind of materials won't. So typically in a metal, it's easy to establish an electric current. That's why we use metal in wires and wiring. But it's easy to establish an electric current because one or more of the electrons in the outer shell of the atoms are not anchored to a nucleus. So essentially they have free electrons that can move throughout the material. And we kind of talked about this already in the previous lecture. And there is a name for that when you have a type of metal that has all these free electrons that can move around. That's called a conductor. And any metal that is a good conductor of electric current, it is also a good conductor of heat. And that is for the same reason. So good conductor of electric current, good heat conductor, and that is because of the loose electrons that we just talked about up here. Now, there's other materials like rubber, glass, things like that. So in these materials, the electrons are actually tightly bound to particular atoms. So although this material might have a lot of electrons, whoops. Although this material might have a lot of electrons, so you got the positive charge, there might be a lot of electrons in some material, but all of these electrons will actually stay put. They're going to stay attached to their host atom. So these materials are poor conductors of electric current, just like they are poor conductors of heat. And that's just because their electrons don't move as well. So these materials are called insulators. And we can actually compare the two here. Conductors are things like silver, gold, platinum, copper, and aluminum. So these are actually very expensive. And you're only going to see those in some of the best types of electronics, the very expensive electronics. Everything else, just like wiring in your house or more industrial applications, you're going to see copper and aluminum just because it's a little cheaper. As far as insulators go, we're looking at glass, plastics, wood. Wood is a good insulator. If you ever see someone like holding onto something and being electrocuted, you should grab a broom and use the broom to push them away from the thing that's electrocuting them, because that way you won't get shocked. Woods are very good insulator. Um, let's see. Yeah, so glass is actually used to keep the large electrical wires from touching metal towers. So if you think about the big towers where you have the cables running, across the mountains and everything, what you'll notice is a lot of times they'll like set on glass or have glass covers where they're actually near or on the metal tower, just because glass is such a good insulator. Um, and then here's a relation between the two. So, like I said, copper and aluminum are low cost conductors. That's why we use them in wires. So you'll notice if you've ever taken apart something electronic or cut some wires, you have the copper or aluminum inside. But then there's also the plastic cover. So you've got your plastic cover, but then you also have the wire inside. So that plastic cover is what keeps you from disrupting the electric current or getting shocked by those wires. You have a conductor wrapped in an insulator. And then just for a visualization of what we talked about last time, you can see here, might be hard to read, but with the conductor, you have all these free electrons sort of zooming around. But then in an insulator, you can see that they're more confined to particular atoms. We'll say confined electrons for insulators. It turns out that some materials are actually kind of in between. Some materials are neither good conductors nor good insulators. With these materials, some of them are pretty good insulators. If they're the pure substance, if you have a particular pure substance in its crystalline form, then it's usually a good insulator. Until you add impurities. Okay, so if you can take something that's a decent insulator, add impurities, and then all of a sudden it becomes a great conductor, well, that is called a semiconductor. And essentially what happens is this process of doping, which is what this is here. Doping essentially allows for electrons to be added or removed. So particular structures, if you dope it, it will go from just being an okay insulator to a wonderful conductor. So essentially a material that can be made to behave sometimes as an insulator and sometimes as a conductor is called a semiconductor. Not a very creative. But semiconductors are actually pretty cool. Semiconductor can actually, some semiconductors will conduct. So basically they will hold a charge somewhere like an insulator. And then when you apply light to it of a specific wavelength, so essentially a specific color, all of a sudden it goes from an insulator to a conductor. So you can imagine a semiconductor would be helpful if you have like something you want to turn off in the daytime. You can use a switch you can use a semiconductor to switch. So when the sun comes out, it becomes a conductor, and that can send a signal to like turn the light on or off in the daytime. I'm trying to think of a good example. Like no. Well, we've got a good example here. I was just trying to think of one that you might see from day to day, be more familiar with. But anyways, a selenium plate, or just selenium in general, is actually a good insulator until light is shined on it. Is shown on it, I guess. So it turns out, as soon as you start applying light to selenium, any charge that it has built up leaks away pretty quickly. So for selenium, it starts as an insulator. It's supposed to be R. Shine some light on it, and then you get a conductor. Really quick. This happens really fast. So it turns out if you have a charged selenium plate that is exposed to a pattern of light, so you can think about in a copy machine or a copier, you know, if you put in an image and then use some light and mirrors, you can actually expose a selenium drum, so a round plate of selenium. You can actually expose it to a pattern of light. So that pattern of light is essentially your image. Okay, now if you take a charged piece of paper, so it's got to have a static charge on it. If you take a charged piece of paper and you place it over the plate and then apply a black powder, well, the powder would stick to where the selenium still is charged. And that's actually the basics of photocopying. So literally what you're doing is you're taking an image and you put it on the scanner, and then light will send that image to essentially not all copiers, but selenium copiers. They'll send that image to a plate, and then where the light isn't is where powder's going to stick. So when you put that image on the selenium plate over a piece of paper, you're essentially using electric forces to bring the ink to the paper and have it stick to the paper. Something else that's definitely worth mentioning while we're talking about electrostatics and electronics, beyond semiconductors. By the way, this was the first type of physics that I ran into as an undergrad that I absolutely hated. I hated semiconductor physics. But anyways, the other thing we need to talk about are transistors. So basically, if you take thin layers of semiconducting material, not necessarily selenium, but maybe germanium, I think that's another one. So if you take layered semiconductors and essentially make a sandwich, you're going to make a transistor. And what transistors do, well, the reason they're important is they actually replace vacuum tubes. So if you've seen old radios or old electronics, like old TVs, you'll probably notice these. They look like light bulbs in there, but those are essentially vacuum tubes. And they're huge, and that's why a lot of electronics are really big. So transistors actually replace these vacuum tubes, and they replace them in a big way. So transistors use one electrical signal to control another signal. So essentially what would happen, down here in picture A in the transistors, let's take a look at this transistor. So you have this common prong, and what's going to happen is you can control a signal on one of them, a small signal, right? You can control a small signal. You can control a small signal on one of them, which will then give you a big change in the signal on the other. So we'll just say big change here. So that's the idea. You're using a small input to control a bigger output with a transistor. Essentially, the simplest transistors will act as just an on-off switch to start or stop some other signal. But what's really wild, and we could talk about this on the next slide, but you can actually make transistors really small and put a bunch on integrated circuits. So this is the kind of stuff that you'll find in your phone and more high-tech equipment. So another type of transistor is essentially an amplifier. You can think about using a small signal input to control something larger. You can even stack transistors in series, and you can get a lot of amplification out of that when you stack them. And these transistors can be so small, as you can see here, these transistors can be so small that a typical smartphone can literally contain billions of these transistors. And that's where you start getting your logic in computers. And essentially a lot of the control and all these features in your smartphone is just driven by all these billions of transistors. And this is no exaggeration, but the transistor really is one of the greatest inventions of the 20th century. It allowed us to replace all these big, bulky vacuum tubes down to something as small as like these integrated circuits that we can just dump inside much smaller technology, like our smartphones. Beyond semiconductors and transistors, we also have superconductors. And it turns out in certain materials, if you can get them at too low temperature, and I mean really low, we're talking almost 0 Kelvin. If you can get them really low, electrical resistance disappears. So they literally can conduct current much easier than just our regular day-to-day wiring or circuits in our phones. These specific materials that are superconductors, they actually essentially have zero resistance. And we'll talk about that a little more in the next module. Um, yeah, these superconductors, they actually, there's no heat loss. They don't heat up when charges flow. So you pretty much get all of the energy you put inside. You don't lose any to heat. So they're wonderful, wonderful, wonderful things, but you have to keep them at very low temperatures. Um, with superconductivity, you get some applications like low loss power power line transmission, where you can transmit more power to homes and stuff without loss due to heat. You also have like the maglev trains. I think there's some in Japan, but they're very high speed because they're low friction, right? They have these superconducting magnets. Ooh, let me use a different color. They have these superconducting magnets that cause them to levitate. And then essentially what you can do is you can alternate the polarity on the magnets. And that's how you can send these trains down the track. Just this alternating polarity will push them forward. So this is actually a really neat use of these superconductor materials. Okay, so we've talked about several different types of materials, but let's back up and just look at insulators and conductors again. If we take a material or two materials and we rub them together, you've done this before, like with a balloon rubbing your hair and you put it on the wall and it sticks. If we take two materials and rub them together, we're going to transfer electrons. Remember, we can't create electrons, right? This is conservation of charge. And that just means we're going to move electrons from one place to the other. Now, when we do this through physical contact, like balloon on your hair, this is actually called charging by contact. Again, not a very fancy name. But when you do it by physical contact, you essentially redistribute charges on an object. Oh, wait, sorry. Nope, that's something else. That's something else. So I'm going to draw this here. So we can do this through physical contact, which is charging by contact. Or we can actually charge an object or redistribute charges on an object simply by putting something charged near it. Okay. So this is actually charging by induction. If you get close enough, you can change the charge on something or you can touch it directly. Okay, so we have charging by contact and then charging induction. And how you know what direction things go is you can actually look at the triboelectric series. So the triboelectric series essentially tells you what's more likely to lose electrons and what's more likely to gain electrons when you touch them together. So you can see here, if you think about the balloon and the hair example, well, hair is up here close to the positive side, so it's going to lose electrons when you do this. Okay, so your hair is going to lose electrons to the balloon, right? Because the balloon is down here where it is more likely to gain electrons. So if you use two similar materials on the same side, you're not going to charge it. If you rub two balloons together, it's less likely to transfer electrons than if you have two different substances or materials from two different sides of the triboelectric series. Okay, now let's get back to charging by contact. When you do this, electrons transfer from one material to another just through that simple touch. That's the name, charging by contact. If the object is a good conductor, electrons will spread to all parts of its surface. Okay, so you can notice this in my first example here. Okay. Notice how the electrons on the sphere, they spread out evenly across its surface. Well, this is because all electrons repel each other. So all these electrons up here, they all want to get away from each other because they're all repelling. So electrons are going to go to the surface of a conductor. Negative to the surface of a conductor. Now, if we try to do this to an insulator will actually charge unevenly because the electrons, they don't want to move around. So if you start charging an insulator by contact, you sort of get clumps. And that's just because the electrons don't want to move around. So you can only negatively charge little pieces of an insulator. Okay, now let's talk about charging by induction. This one's a little more tricky. And this is essentially charging something without physical contact. All right. First, let's consider conducting spheres touching one another. Okay, so we have sphere A, sphere B. They're conductors. And if you put them together, they essentially make one big conductor. Now, if we take a charged rod, like a rubber rod or something from that list that's more of an insulator, we can place it close, but not touching to one side of spheres A and B. Okay. Now, what happens is the electrons, they're going to get repelled, right? Because you have electrons here. They want to repel each other because they're like charges. They're going to spread apart. So that means we're going to have a net positive charge over here near the rod. So we have a positive charge here, negative charge here. Now, once that happens and we separate those charges, we can then separate those spheres. And they've both been charged. They were acting as one conductor, but then we split it in half. So once you split it in half, you can't transfer those electrons back and forth anymore. So once it's split, sphere A keeps its positive charge, and then sphere B will keep its negative charge. And this whole process, this occurred without touching the spheres with the rod. So that's charging by induction. Yes, the spheres themselves were originally touching, but the induction part, that happened here. You can actually see this during a thunderstorm. So what happens is the negative bottom of clouds will actually charge by induction the surface of the Earth. So you're going to get electrons actually pushed downward, leaving a positive charge at the surface. And that's where you can get that, that inductive charging during a thunderstorm. So you might have seen videos of people's hair starting to stand up during a thunderstorm. That's really bad because that means you could get struck by lightning. But essentially what's happening is this inductive charging. The last thing, charge polarization. So we talked about charging by conduction, charging by induction. We can actually charge by induction on an insulator as well. So it's not just restricted to conductors. Usually you see it done with conductors, like air conducting spheres. But in this case, when a charged rod is brought near an insulator, there aren't really any free electrons to move around. So what that means is we're actually going to charge by polarization. So instead of pushing electrons all around the substance, we're just going to scoot them. We're going to shift them a little bit. Okay, so this is where that rearrangement comes in. Essentially, the electrons around an atom. So if you think about the positive nucleus, electrons flying around, the electrons around an atom are essentially slightly pushed to the side. So they kind of get pushed over here instead of being nice and orbiting around the whole nucleus. What that means is one side of the atom will be just a little more positive and one side will be just a little more negative. And this is electrical polarization. So you can see here, when you bring in this negative charge, you're going to push all these electrons over. You can see where they're starting to get pushed. So this is like an atom or a molecule. And all you're doing is essentially just sort of pushing the electrons over. So then you have the positive nucleus, and then the electrons sort of push over to the side. You'll notice that all the way down through here, that makes a positive surface. So you're essentially getting a bit of a surface charge on an insulator just from induction and pushing those electrons over. This is actually why a comb attracts uncharged pieces of paper. So you could have a neutral piece of paper, you charge up a comb. So the force of the attraction will essentially separate the charges. You'll notice that here, remember, it's the electrons that move. So you get all these electrons moving over to the positive charge at the comb. And you'll also notice that the force in between the positive and negative is a little bit larger than the force over here, because you've also got positives here and positives here. So they want to repel, right? This side of the paper is repelled because like charges. Ooh, does repelled have two L's in it? It might. But the closer side, because it has opposite charges, is attracted. Now, you'll remember Coulomb's law, which describes the force that these two sides of this paper is going to feel. And because this one's closer, remember, Coulomb's law depends on distance, right? So the negatives are closer, that force is going to be stronger. This positive side over here is further away, so it's going to be weaker. And this is essentially what happens when you like rub a balloon on your hair and you put it up against the wall. You're essentially polarizing. You're polarizing those molecules that make up the wall. And this is how microwaves work. If you put your food in a microwave, it turns out that water molecules are slightly polarized. You can see here the hydrogen atoms, they're positive, or they hold the positive charge. The oxygen holds the negative charge. So you get a little bit of a difference here between the positive and negative. So you make a little dipole. Dipole. And a dipole is essentially this right here. Just where you have a positive charge on one side and negative on the other. Okay, so what happens is when you apply an alternating electric field that alternates really fast, and we'll talk about electric fields in the next lecture, but when you apply an electric field, what happens is that acts on the dipole in the water molecule. So you get your electric field started here, you got negatives, you got positives. Then when you alternate it, it causes your water molecules to jiggle. And that's actually what heats up your food in a microwave. All right. So that's got conductors, insulators, semiconductors, transistors, superconductors, charging by contact, charging by induction, and charge polarization. So this is, so far in this module, we've talked about where the charges come from, positive, negative, electrons, protons. We talked about Coulomb's law, the force between these two charges. And then we've pretty much just talked about how we can move these charges around and actually add them or take them away from different substances. So next, we'll talk about the electric field and electric potential. And all these things are going to lead us up to actually talking about circuits and dealing with sort of the everyday circuitry that you see when you turn on the light switch or things like that. So in the meantime, if you have any questions, don't hesitate to ask.